in the last class we have already discussed about stationarity of a random process, and we started describing this arrival process as a stationary random process, and then we started giving two very important properties of this particular process, and this process will later on see that it actually talks about a process which is called Poisson process or Markovian process. So, we will start describing about these. Okay. So, let us try to understand. So, basically if we go back to last lecture, what we have started describing is the two things. One is called independent increment and the other one is non-simultaneity principle. So, already we have seen what we mean by non-simultaneity, some basic definition of that we have given. So, these are two very fundamental property of this Markovian or Poisson process. What are they? One is anyway fundamental, that depicts the event occurrence. It says that it is non-simultaneous, that means whatever happens, no two events in this world can simultaneously occur. Okay. So, this is one principle. Second principle is not so fundamental probably, but for this Poisson process this is absolutely required, where it says that it is a description where things of future depends only on present and do not depend on past. Okay. So, with that you will see just these two things, these two definition that we have given, just from these two definition we will derive the Poisson process. That is the strength of this particular process. So, that actually says that Poisson process does not require any extra description. So, it has only important criteria, which is that first point, that is very typical of Poisson. Because of that point it has become Poisson, okay, because this is fundamental to any event or any arrival. Okay. So, any arrival, this non-simultaneity principle will always be true, but independent increments is the property of Poisson process, and we will probably I do not think this course has that bandwidth of proving that Poisson will be able to show that this memoryless property that we have talked, Poisson is the only process in continuous time of course, which describes memorylessness. No other distribution is possible, and for discrete it is geometric. So, other than these two, okay, there are no other process that you will be able to describe which has memoryless property. Okay. So, that is a very fundamental things, and this is therefore, this is very fundamental to this memorylessness. Let us try to understand these two things little bit more mathematically. Okay. So, in mathematical term what we are trying to say, first we in any time instance where there are events which has occurred. So, we are trying to get some intervals. The first criteria of these two intervals are they must be independent or non-overlapping intervals. Okay. So, that is a very fundamental thing, that they should not be overlapping. Okay. They might have common boundary. So, I can start from here. So, basically I can define my these two intervals with common boundary, but generally what we should avoid is that they should not have overlapping instances. And then what I can say is whatever we are observing. So, there are random things happening. So, I might get count over here, okay. I might get some other things, that what are the arrival time between the arrival that has occurred. So, these kind of different things I can get, all are random properties. Okay. So, if I take count, let us say the one we were describing was count. So, if I say count, then how many count has occurred over here, statistically that has no relevance to how many counts I will be observing over here. That means, these two are statistically independent, and that is why they called independent increment. So, we are actually incrementing the time from here to some other time, and those incremental times that we are discussing, that statistically independent from the previous one. Okay. So, that is why we call it independent increment. That means any statistical property we define. So, suppose probability of count we want to define P n over this interval, let us say this is T 1, this is T 2, this is T 3. So, over this interval T 2 minus T 1 or T 2 comma T 1, T 2 to T 1 and P of let us say over here n 1 and this is n 2, which is T 3 comma T 2. So, these two are independent. Okay. What does that means? Mathematically, their joint distribution will be separated out, they will be multiplied. Okay. So, that is exactly what will be happening. So, that is the mathematical definition we get from here. You will see that from our in our derivation we will be using this property. And independent increment later on you will also see that actually gives us the memoryless property, we will also prove that. Okay. So, this part we will do, we will try to see that independent increment, what is the consequence of that, and we will try to say that this independent increment is actually responsible for this memorylessness. We will also be able to prove that, okay, once we do the derivation of course. So, this is one thing. Next, let us try to understand this non-simultaneity principle, what is the associated mathematical description of that. So, that is something we will be doing now. Okay. So, now let us try to see this non-simultaneity principle, what does this means. So, again mathematically let us try to define it. Now, let us call a probing time interval of interval delta t. Okay. That probing can be happening at any instance. So, I can probe it over here for a amount of delta t. I can also probe it over here for a amount of delta t. I can probe over here for a amount of delta t. Okay. So, I define this probing interval of delta t and I try to gather the statistical property. Okay. What is my statistics over here we are gathering? It is the count. So, that means within delta t how many arrivals has happened. So, over here if I just do a bookkeeping, over here 2 arrival has happened, over here 1 arrival has happened, over here 0 arrival has happened, like this. If I keep on doing this probing, I will see different kind of, because it is random. So, different kind of things I will be getting. Okay. Now, because of this non-simultaneity principle, so you can carefully see how we are coming to this non-simultaneity principle, its mathematical definition. If we start making this delta t tends to 0. Okay. So, if you do this limiting condition, that means my delta t, that probing interval is becoming infinitesimally small. Now, because of non-simultaneity principle, when delta t is vanishingly small, can I observe anything other than 0 and 1 arrival? Can I observe? Because earlier for this finite amount of delta t, where it was not we take some value and it was not going to 0. Okay. So, at that point I could have said any value is possible, I can have 3 count, 4 count, 7 count, everything is possible. But when I start making delta t vanishingly small, then I can see because of the non-simultaneity principle, I will have only either 0 arrival or 1 arrival. So, whenever it is probing, it is so small that either it will probe nothing or it will probe only 1 arrival, because even if 2 arrivals are very close by, my delta t can be even smaller than that, so that it will skip the other one. So, therefore, I can only have either 1 arrival or 0 arrival, okay, if I make this delta t tends to 0. So, this is the essence I will try to bring in. Okay. So, let us try to see how do I bring in this principle. Okay. So, for that, let us say I have a stationary process. If I have a stationary process, what is the arrival rate? That must be constant over time, and that we have called lambda. So, that means lambda number of arrivals are happening for a unit. When I make this delta t to be 1, let us say 1 second or 1 millisecond, whatever is my time unit. So, over that lambda number of arrival will be happening, whatever the value of lambda. If lambda is 2, that means 2 arrive, remember it is average arrival. So, it will not be every 1 second you take, everywhere 2 arrival will be there. It is just that will be the average. You take multiple such things, you average it, it will be coming close to that lambda value, and this will not be varying over time. So, if we take ensemble averages, it will be always similar at every time instance. Okay. So, let us say this lambda is my arrival rate, right. Now, let us try to understand. Suppose I have taken a very big time, let us say that is capital T. Okay. So, this very big time I divide into small unit of delta t. Okay. So, basically I am defining my probing times. Okay. And if delta t tends to 0, then how many such intervals will be there? That will go towards infinity. So, if that count is capital N, so n goes to infinity. So, if I keep counting, so this is my first interval, second interval, third interval and so on. If last one is the nth interval, so n will go towards infinity. Of course, that will be happening because delta t goes to 0. So, therefore, number of intervals will be increased, and this t is very big, I should say. Okay. So, now let us try to understand how many such intervals are there. So, that n I want to characterize. N must be equal to t divided by delta t. Of course, that defines these things. So, whenever n goes to 0, delta t goes to 0, n goes to infinity. So, this is my basic definition. Okay. Now, let us try to understand, if t is sufficiently large, then within this time capital T, how many arrival will be happening? On an average, lambda arrivals happens per unit time. So, in t time, how many arrivals will be happening? So, number of arrival, if I count, that should be lambda into t, because lambda arrival per unit second or unit time. So, in t time it will be lambda into t. On an average, if t is sufficiently large, then this averaging will come to be true, and this will happen to be lambda into t. So, that is why I have to take a very big t. Okay. So, basically I can almost surely say, as long as t is going towards infinity or very big, then I can say surely with the law of average, or we should say this frequency definition of probability principle, or the definition of average, this many arrival will be happening, lambda into t number of arrivals will be happening inside this. So, that means if I now try to say, if my delta t is very small, how many, either it can have 0 arrival or t arrival within this delta t's, because they are infinitesimally small. So, there cannot be any other things which is possible. So, either there will be 0, no arrival, or there will be 1 arrival. Okay. So, these kind of instances will be there. Okay. So, therefore, if I now try to calculate probability that 1 arrival has happened in delta t, okay, or delta capital T, sorry. What is this value? Probability 1 arrival has happened. That is actually, if you now count, so probability is also, probability has a frequency principle. So, frequency principle means all possible cases, that should be in the denominator, and numerator the favorable cases. So, what are the favorable cases of 1? If you count over here all this infinite, almost infinite number of cases, if you try to just see how many arrivals are happening, which are means 1 arrivals are happening, or favorable case to your probability definition, that will be, actually there are lambda into t arrivals overall. So, that must be distributed over here. So, lambda into t favorable cases must be there. So, lambda into t, and how many total possible cases, total possible intervals, how many are there? That is n, which is t delta, sorry, t by delta t. So, this is n, which I can write as lambda t divided by t, just put this definition, delta t, t gets cancelled. Immediately, as you can see, what we have got, if we now generalize it, that probability that one arrival happen in some, instead of capital T, now I give a general definition, in some small delta t time, that will be always lambda into delta t. This is our first definition. Okay. That is what we are saying. But over here I have another condition, that I have to put limit this delta t tends to 0. This can only happen when delta t goes to 0, otherwise not, otherwise this calculation is wrong, because then there will be lot of 2 arrivals, 3 arrivals which we have not accounted in this derivation. We have done this derivation, this entire thing assuming that only 2 cases are there, either one arrival can happen or no arrival can happen, and accordingly we have taken all these one arrival counted as favorable case. If some of this one arrival clubbed into 2 arrival, 3 arrival, that has to be subtracted, but I have not done that. So therefore, this calculation is having some error if delta t does not tends to 0. How do I account for that? What I can say, that this p1 delta t, this must be a regular function. Okay. So this can be defined as a polynomial. Okay. So always I can define it as a some polynomial, it can be anything, I do not know. So some polynomial whose coefficient has to be decided. So how do I put that polynomial? So I can put that to be some, let us say lambda delta t plus some c1 into delta t square plus some c2 into delta t cube and so on. I can define it. Okay. So of course it should not have any constant value, this polynomial, because if delta t is 0, I cannot get one arrival. So basically in a 0 time I cannot have one arrival within that. Okay. So this is fundamentally known, that if my interval is 0, how can I catch an arrival, because that is a point. Okay. So therefore it should not have this polynomial, this generic polynomial should not have any constant. Of course I should not put lambda over here, so maybe I will put c1 over here, c2 over here, c3, something like that. Okay. Some general polynomial. Now what I have seen, that if limit delta t goes to 0, then this happens to be this one. So therefore as you can see, this must be, this c1 must be lambda delta t, and this particular portion must vanish. What does that means? If I define this to be a polynomial O delta t, then I can write this p1 delta t to be some this lambda into delta t plus some higher order polynomial of delta t, and what is the definition of that? That this O delta t means this portion goes to 0 when delta t goes to 0. Okay. Or rather I should say that if I divide this, not only this goes to 0 when delta t goes to 0, also I should see that if I divide this whole thing by delta t, it must comes to lambda 1. Okay. So therefore what I can do is, this is a higher order polynomial of delta t square, delta t cube and all those things. So if I now divide this by delta t, so this O delta t, the definition is, if I divide it by delta t and then take the limit, this must be vanishing. So that is the definition of this order. Once I give that definition, now my overall things are clear, because now I can, without putting this condition, I can make this definition. Only thing is that for this one I define a separate thing, so that I am safe. I can always say whatever delta t I take, this is the value. Only thing is that if delta t goes towards 0, this will anyway, this particular part will be vanishing and I will get this definition, my actual derived definition back. So therefore I can safely say that this is the now usable definition that we can create over here. Okay. So, we have got some probability term. Remember, with all this principle, our target is to characterize the stochastic property. So, that is exactly what we are trying to do over here. We are trying to characterize that stochastic property. Okay. So, we have got something now over here, that P1 in some interval, that means probability that one arrival will be happening, that count will be 1 in that arrival delta t is actually nothing but this lambda, which is I already know that it is stationary. So, that stationarity has to be another property actually. That is the sum, that is something I have already discussed in the even before these two fundamental property, right. So, stationarity you can always say that is the third property actually. Okay. So, stationarity has to be satisfied. Once the stationarity is satisfied, then lambda I can fairly take, okay, and that should not be dependent on time, and therefore, I can define this equation which is calling that probability that one arrival happening within a particular interval delta t, okay, wherever that delta t is defined in time, and it has a higher order polynomial which has this extra definition. Okay, good. Now, let us try to define what is probability of n t or n delta t where n is anything greater than 1. It might be 2, it might be 3, it might be 4, something like that. In general, if I put this limit delta t tends to 0, where it will go? What is P n delta t? That must be 0, because there are no favorable conditions or no favorable cases. Again, if I try to calculate this one, what is the probability that within delta t 2 or 3 or 4 arrival will be happening? All are 0, because nothing, because of non-simultaneity principle, if my delta t goes to vanishingly becomes vanishingly small or goes to 0, then I do not get any 2, 3, 4 arrivals within a delta t. So, therefore, those should be 0. So, this must be all 0, but that is only true when delta t goes to 0. So, therefore, again similar definition I can give. I can always define that P n delta t is a polynomial which vanishes to 0 whenever we put delta t tends to 0. So, therefore, again P n delta t I can define with the same principle as O delta t, where O delta t has the same definition as this one without giving this. So, now we have got two definition: probability that one arrival is happening, that is this one; probability that n arrival, n anything greater than 1, that is this one. Let us now try to see, only thing that is left is 0 arrival. So, what is the probability that 0 arrival will be happening in delta t? Because we have calculated all other probabilities, it is just 1 minus all those. So, 1 minus probability that one arrival will be happening and minus summation over n probability that n delta t will be happening. Okay. Now, if I just put 1 minus lambda delta t minus O delta t, and this is also summation of O delta t and this O delta t, all together if you sum them, that will remain another O delta t, because what will be happening? Let us say some O1 delta t and O2 delta t we sum, all that will be happening, they are polynomial of second order and higher, their coefficients only will be differing. So, if this I write as C1 delta t square plus C2 delta t cube dot 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 dot, and this if I write as C1 dash new coefficient delta t square C2 dash delta t cube dot 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 dot, I can always write this sum as C1 plus C1 dash a new constant delta t square plus again C2 plus C2 dash a new constant of delta t cube, which is nothing but another O delta t. So, therefore, I can write this whole thing, that one delta t coming from here and these all delta t's, their summation I can just write as another O delta t. Okay. So, therefore, that happens to be my definition of P0 t, P0 delta t. So, what we have done, almost just by this non-simultaneity principle we could characterize the whole thing. Okay. We could mathematically define the whole thing. What are the definition? If we just summarize, so P 0 delta t is nothing but 1 minus lambda delta t plus O delta t, P 1 delta t, that is lambda delta t plus O delta t, and P n delta t is equal to O delta t for all n greater than 1, with additional definition of limit delta t tends to 0, O delta t divided by delta t is equals to 0. That is the overall mathematical definition of the non-simultaneity principle. So, now we have understood two things. We could define the non-simultaneity principle taking the assumption of stationarity. We could also mathematically define, earlier we have seen that independent increment. What we will be doing in the next class is taking these two things, we will try to derive the associated arrival process which follows these things, which is stationary, which is non-simultaneous, these two things, okay, that is by definition, and it has this independent increment. Okay. We will see that just by taking that independent increment, the Poisson distribution will be automatically derived from these three principles. Okay. So, that will be our next discussion. So, till then, goodbye.